Alright, welcome to the second part. So this chapter 5 that we are covering is called Characterizations of Bricks and Braces. And what we are done with is bricks. ELP theorem is basically a characterization of bricks. They are precisely as three connected by critical graphs. Braces of course are easier, which is why I will just state the characterizations of braces. Oh, I forgot the mic, thank you. Yeah, am I audible? Yeah. Now is it working? Now it's working. Okay. Yeah. So so characterization of bricks we are done. Three connected by critical graphs. Braces are of course easier, being bipartite, and I'm just going to state the characterizations of braces that are well known, and they are basically all easy exercises at this point in the course. What are braces? They are basically bipartite matching chord graphs that are free of non-trivial tight cuts. So we have already characterized tight cuts. So going to graphs free of non-trivial tight cuts can be so difficult. Right. So anyway, so characterizations of braces. Let's see. For a bipartite matching covered graph H, or I don't know, GAB, the following are equivalent. One, G is a brace, which means it has no non-trivial tight cuts. Well, let's look at non-trivial tight cut. We know what it looks like. Non-trivial tight cut looks like this. All edges go like this, this, and this. In particular, how large is the neighborhood of this set? Plus 1. Its cardinality plus 1. And do you agree that if you find a set whose neighborhood is just one more than itself, then that is the shore of a tight cut? Well, it may not be the shore of a non-trivial tight cut, because this side may be a single vertex, right? But otherwise it will be the shore of a non-trivial tight cut, right? So in fact you get a Hall type characterization for any set, for every set of, let's say, the A vertices. We will qualify, we'll make that more precise later. What do you think should be the neighborhood cardinality? Should be at least plus 2, right? Plus 2. Well, it can't be plus 2 for the empty set, and it can't be plus 2 for almost everyone but one vertex. So therefore S is not empty, and cardinality of S is less than or equal to A minus 2. For all such subsets, the neighborhood should be at least 2 more than its own cardinality. Number 3. If you remember in bipartite matching covered, we had a similar statement. For a bipartite matchable graph, the following are equivalent. G is matching covered, neighborhood is at least plus 1 more, and we had a third thing. If you delete any white vertex and black vertex, then the remaining graph has a perfect matching. Here, what do you expect? Instead of deleting one, you delete 2. 2 white and 2 black. Turns out G minus A1 minus A2 minus B1 minus B2 is matchable for all distinct A1, A2 in A and B1, B2 in B. And turns out, well, this is actually suggesting that here we are not saying anything about these vertices being adjacent or not. But well, if A1 and B1 are adjacent and A2 and B2 are adjacent, then what does it mean? These two edges extend to a perfect matching. So in fact, it is also true that each matching of cardinality 2 extends to a perfect matching of G. In other words, any pair of non-adjacent edges, they participate in a common perfect matching. Turns out all these 4 are equivalent. Did I make any mistakes? No? All good? Yeah.
Second point for C4, it doesn't hold.
The second point doesn't hold for C4. There are no such sets, no? There are no non-empty sets whose cardinality is less than equal to 2 minus 2, 0.
Okay.
So it will be vacuously true.
Other one takes care.
Right, this one is fine. Yeah, this second condition takes care of it. Yeah. No, this is actually a good point because, well, the reason I wrote bipartite matching covered is to kind of not fall into these traps. You can try to make this assumption weaker. You can say for a bipartite matchable graph, or you can say for a bipartite connected graph where cardinality of A is equal to cardinality of B. But then some of these statements you'll have to be careful. They may not go through. I'm not sure which ones. I don't want to try it. So I'll just assume the graph is matching covered. Because anyways I know how to check the graph is matching covered, right? So for a bipartite matching covered graph, these are equivalent. Is it true? Are all of them equivalent? Yeah, Amit is the expert here. He spent a lot of time, but you don't allow K2 to be matching covered, right, in your thesis? K2 is not matching covered in your thesis. 4 vertices at least. So now you have to consider K2 also. Everything goes through? Yeah? Yeah, okay. Yeah, some of them will become vacuous. For K2, all these 3 are vacuous. There's nothing to be checked. Or any 2 vertex K2 up to multiple edges. Okay? So these are all easy. DIY. Okay? Figure out what is the best order. So generally for such a statement, you don't want to prove every single double implication, right? What you want to do is you want to figure out a cyclic order. 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 1. Right? So figure that out yourself. Good. One point I want to mention here is that matching covered graphs in the literature, I might have mentioned earlier, matching covered graphs have also been called one extendable graphs. Because every edge extends to a perfect matching. Some definitions include connected, some definitions don't require connected. But I will just say matching covered graphs historically have been called one extendable graphs. Because of this reason, braces are bipartite 2 extendable graphs. So this is the reason why braces in the literature have also been called 2 extendable bipartite graphs. It turns out that there is actually a lot of work on k-extendable bipartite graphs where the definition is obvious. every matching of cardinality k extends to a perfect matching. Typically, you include some additional conditions. Amit can tell you more about that. I won't bother. You include some additional conditions for corner cases and all that. But in general, k-extendable means every matching of cardinality k extends to perfect matching. So for bipartite, in the bipartite world, there is a lot of results on k-extendability. These are not included in Lucchesi and Murty. If you want to read about that, you can read Lovász Plummer. Lovász Plummer has a lot of stuff, and Plummer in general, Michael Plummer has a lot of work on bipartite k-extendable graphs. However, in the non-bipartite case, we know very little. Well, we know that they're all matching covered. In fact, you can prove that non-bipartite 2 extendable graphs are actually going to be bricks. But beyond that, we don't know much more. And it is not if and only if, right? Bricks need not be 2 extendable. Yeah. But yeah, anyways, there's not much known about non-bipartite k extendable graphs or even k equal to 2. Right? But anyways, so that's, and yeah, if you're interested more in these things, please talk to Amit. His entire thesis was on, well, first part of your dual degree thesis was basically on k extendability of bipartite graphs. Well, yeah, okay. So with this, we conclude chapter 5. We have characterization of bricks. Now we have characterization of braces, and there is one more thing that is there in this chapter, which is they give a complete characterization of tight cuts in matching covered graphs with exactly 2 bricks. So let's just do a quick recap. 0 bricks means bipartite. All tight cuts are barrier cuts. They look like this. 1 brick means near brick. Right? Near bricks are matching covered graphs whose b is equal to 1. There, every tight cut will basically look like this only, but only one side we know. In a near brick, every tight cut will look like this. One side will be bipartite, therefore it will look like this. The other side will actually not be bipartite, therefore it will look like whatever this is. Right? So b equal to 1, b equal to 0. What about b equal to 2? Is there a complete characterization of tight cuts? Turns out there is. They look very similar to barrier cuts and 2 separation cuts, but there is a generalization of 2 separation cuts. We will not prove this in this course, but I will just show you an example. So here is what, instead of a 2 separation cut where I have a single vertex and single vertex, now I will put some bipartite creature here. This is what these are called, essentially 2 separation cuts. This is not K1. If you put this as K1 and this as K1, it becomes a 2 separation cut. But what it is you have taken a 2 separation cut and you have spliced each of those vertices U and V of the 2 separation with some bipartite creature. That will give you this kind of a graph. Turns out, essentially 2 separation cuts. You can read the exact definition in Lucchesi and Murty, but this is basically what it is. And what they prove is that if G is a matching covered graph, number of bricks is exactly 2, then every tight cut is either a barrier cut or an essentially 2 separation cut. And this is actually used in some future chapters, but I think those chapters are like 16 or something, so we may not actually need it right now, right? So this is a complete, and essentially 2 separation includes 2 separation. So 2 separation cuts are essentially 2 separation cuts. In fact, they are very 2 separation. Right. So that's what, that's one more result that is proved in this chapter, but we will skip it for now at least. If we have time in the course, eventually then we may cover it, but I don't think it is going to be feasible, right? Yeah. And let's look at one quick example. Peterson graph minus one edge. This is Peterson graph minus one edge, and here is your essentially two suppression cuts. Sorry, same color. But these are essentially two suppression cuts. This bipartite graph is very small, but in general you could have a larger bipartite graph here. Okay, so that's all for chapter 5 of Lucchesi and Murty. The next is chapter 6, which is the perfect matching polytope. So we will be doing some discussions that may be somewhat more algebraic in nature. Right? There will be some vector spaces and some polytopes coming into the picture. Right? Okay, and we will see how this perfect matching polytope ties very nicely with the tight cut decomposition. And some of the things, I think most of the things I'm going to cover, many of them actually I've not taught before, so should be fun for me also. Okay, thank you. Any questions, concerns? All good? Alright, thank you. You can stop the recording.